In our last demo, we talked about and showed how to create a basic verifiable log in the shell user interface. This time we'll look at how to create a verifiable map and some of the operations that we can do with that. So again, we're starting off on the shell page under Manage Account. We previously created an access rule, so let's select the access rule that we created. And here, similar to the logs, we can either create a new map, we can list any existing maps, and we don't have any yet, or we can load an existing map by name. So let's create a new map, call this demo map. Similar with the logs, the map names that we select here are unique within our account. So they're effectively namespaced by the account number that we have. So let's create the new map. Then now that we've created it, it's been pre-selected for us, and now we can perform operations on that map. We can set, so basically when we get a map starts off as empty. So for any single key in that map, it has an empty value. So as a write operation, we can set values in that map for specific keys. And by doing that, that creates a mutation that applies to that map, and then we can see that reflected. So we'll go through and we will create some entries in the map. We'll then look at how to look at the tree head for the map, which is similar to the tree head for a log, where we can see a summary of the Merkle tree root for all of the data that's held in a map for a particular time. And then we'll look at how we can look values up in that map, where we can see a verification proof to show how the value that we receive is included for the root hash in that map at a particular stage. Finally, one of the interesting things about maps is they're actually effectively sandwiched between two pairs of verifiable logs. When we add an entry to a map, rather than affect the map directly, we first add that to a mutation log. And the map itself reflects the set or the list of entries in the mutation log evaluated at a particular point. And then finally, the map root hashes that we generate after applying those mutations, we take those, we pair them up with the root hash of the mutation log at the same point, and we write those to a tree head log. And the reason we do that is so that clients can efficiently verify that the map root hash that they have received is included in that tree head log. And if they do that, then they can have confidence that anyone who is auditing the tree head log to ensure that all of the map root hashes are calculated correctly, they can have high assurance that the map is not misbehaving. So let's get started. Let's go and create, put a value into our map. So go to set key value. Let's get the value key foo, put in the value bar, and we'll hit add as raw data. Similar to add as JSON and redactable JSON, we'll do a further tutorial on how those work. So for today, we'll just focus on raw data. So we click add, and this will come back to us with effectively a receipt to say that we've received this. We're queuing this up to put in the mutation log, and at some point soon that we added the mutation log, it'll be sequenced in there, and then the mutation log will be applied to create the overall map. So let's create a number of keys and values. Let's go key foo. We'll make that foo 1, bar 1. Not feeling very original today. We'll go 2. Oops, 2. 3. 3. Should have 4 mutations so far. And now let's just go back and let's change the value of foo. Remember it was bar. Let's change it to baz, and we'll add that as well. And again, we'll get a each time we add that, we get a leaf hash back for the mutation log entry. So we've added these entries to the map. Let's go back now at the map and sort of look at how these are reflected in the mutation log and how we can get those from the map. So we go back to choose operation, which will bring us back to the previous screen. And from here, let's have a look at the tree head for the map. So we go to get tree head, and similar to getting the tree head for a log, we give it the size for which we want the tree head. We'll select head, which will give us the latest one that's available, and we'll click fetch. So this will come back, it comes back with two values. It comes back with the root hash for the map, which is the FOW value. And then we also come back with the root hash of the overall of the mutation log at that point as well, which is the QLU entry that we have here. And finally, it reflects the size for which this is valid. So this is saying that for a tree size of 5, so after 5 mutations have been received, this first value is the root hash for the map at that point, and the second is the root hash for the mutation log. So now let's go and say, okay, we've fetched this root hash. Now let's get a value and make sure that it has a proof that shows that the value returned for us for a particular key is reflected in this root hash. Let's go back to choose operation. We'll say get verified value. We can put any key we want in here. Let's put in foo. We're expecting the value baz to come back, and we'll fetch that. And again, we can select a tree size. So we have the value. Baz has come back for tree size 5. We can see, and what we have beneath here, and let's just scroll down a bit so we can see it all. This is an inclusion. This is sort of similar to the inclusion proof diagrams that we can see with the logs, but here we're actually showing an inclusion proof diagram for the map. And the interesting thing about the Merkle tree that we use for the verifiable maps is the Merkle tree we use is actually has 2 to the 256 nodes. So this is an absolutely huge map. That said, it's empty by default. So nearly all of the nodes in this map are set to default calculated values. And so we're not showing those in this diagram here. We're only showing the entries in this diagram that are the ones that have been returned in the inclusion proof for this entry. So if we look at the value baz and we look at the turquoise value down here, SG1, blah, 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 that is the leaf hash of baz. So if you get the null character 0, BAZ, take the SHA-256 sum of that, you get this value. These sort of brown values here are values that we've calculated. So the BJQ value we get quite familiar with. This is the leaf hash of an empty entry. So it's saying that the next entry is empty. So whichever key would have evaluated to the sibling for the key for foo lives out here, and there's no value there. We show how those are calculated together. We then skip 253 different tree levels. We could show them all on the page here, but it would be pretty meaningless. We just have a bunch of calculated values that have the default leaf hash for those entries. Those then get paired up with these red entries, and these red entries are the ones that, or amber entries are the ones that are returned as part of the verification proof for this entry. So when the server returned the value baz, it also returned the tree size because we requested head, and it also returned these amber entries. And these amber entries we can apply in combination with this value baz to produce this root hash. And this is the same root hash we saw before, F0W, etc., etc. And if we were to go back and request this at tree size 4 instead of head, if you recall, we had a different data, we had a different value at that point. So let's hit fetch as raw data. And this will now come back, instead of the value baz, we have the value bar. And we can see here, again, similar thing, we've returned the sort of sibling hashes, subtree hashes that we've needed at these particular points to produce that same inclusion proof. So now we can see the tree hash is different. It's 1L6. And if we now were to go back, for example, go back choose operation, let's get the root head for size 4, and we should see that same value come back. 1L6. So this is the same root hash value that we saw as before. So what we've showed so far is how we can add entries into a map and how we can get verified values back and how those change over time. One other interesting thing, just while we're on getting the verified value, I mentioned before that by default it's an empty tree. We can ask for any value. So let's ask for any value. Let's ask for the value for key foobar. Now that's not something that we've actually entered in there. But we can still request a value come back, and here we can see we get an empty value back, meaning there is nothing in there right now. And again, we get here in the turquoise is the value, the empty value BJQ. Here is its sibling, which is calculated our 253 default tree levels, which we don't show. And here the amber ones are now applied on the left because that's the position at which the key in the tree in which foobar occurs. but we see those other inclusion proof entries returned here to produce that same root hash. So it really doesn't matter what we put in here. For that same tree size as 4, we'll always get the set of entries back that we need to produce that same root hash 1L6. And that's what we mean by a verified value. No matter what we return, we can prove that it summarizes up to that same root hash for the tree. So if we go back to our demonstration map to choose the operation that we have on it, we've looked at setting values, we've looked at retrieving a value, we've looked at retrieving a tree head. The two other components are the substructures, this pair of verifiable logs. And so what we can do from here is we can switch to a view where we can look at the various mutations, the mutation log for this map, and we can switch to the tree head log for this map. So let's have a quick look at the mutation log. If we switch here, we now get the same set of log operations that we could for a verifiable log that we created ourselves. The only difference here is that we can't add to this log directly. If we want to add to the mutation log, we need to call set on the overall map, which has a side effect of adding an entry to the mutation log. So here, let's look at the tree head for the mutation log. And this will return Q, L, U, etc., etc. This is that same value that we return as part of the root hash for the map that we saw earlier. And this is really useful if you are using a map. You will get the state for the map. Because we have the log here, we can use the same consistency proof as before to prove that the mutation log is append only over time, which is of course a property that we want for our verifiable map. If we look at some of the entries within that map, let's just fetch the entries. We'll get all those back. I'm going to click the Fetch as JSON button. Again, we'll go through a tutorial later where we'll explain a little bit more what the differences between the JSON and the raw data are. When I fetch this, we can see here are the 5 mutations. If we look at the entries that go on the mutation log, everything has a timestamp, an action. Here the action we have is set. We have a number of actions that are growing over time, but set is the most basic, most common one. And then next to that we have a key and a value for each. And we return those as strings in the JSON. Those are both base 64 values because these could be arbitrary bytes. And the keen observers will note that foo is this capital Z M9V and so on. So here an auditor of the map can get the full set of mutations, and they can replay that set of mutations and verify that the server is creating the correct value for the root hash for the map. And again, like our other log before, here we just show a diagram to demonstrate how the Merkle tree is calculated for that mutation log. And so again, similar as before, we can do consistency proofs if we want to prove that this is growing over time from mutation 1 through to head. We can get a consistency proof, and we can get an inclusion proof. So if you recall, when we originally added an entry to the map, we were returned a leaf hash. That leaf hash that we were returned is the leaf hash for the mutation log entry. So if we want to ensure that a particular set operation has occurred on the log, we can poll until such time as the mutation log for that map confirms that that mutation has been added in that manner. So if we go back to choose operation, we can switch back to the parent map. And sort of the last part we have here is the tree head log. While a client can very efficiently prove that the mutation log is append only over time, an individual client cannot as efficiently prove the correctness of the map root hash. That requires replaying of the operations in the map. But by ensuring that the map root hash that they receive is entered in the tree head log, which it can very efficiently prove, an individual client in that manner can rely on an auditor to perform this operation. So it's really important that clients do go to the tree head log and they do make sure that the tree head published by the map is in fact included in that tree head log. And we can look at that here. Again, if we switch to this, we get that same sort of log reader in the operations. We obviously can't write to this log directly. It's a side effect of modifying the map. But here we can fetch the entries. Let's have a look at all the entries again. We'll do that as JSON. And we can see here 0, 1, 2, 3, and 4. We happen to have the same number here as we do mutations. We can see for tree size 1, we have the map hash of this value and the mutation log, the tree hash of this particular value. And we can see these are included in here. And again, in this matter, a client can very efficiently get an inclusion proof to verify that the map root hash that they have received is included in the tree head log and that that tree head log is moving forward in time. So what we've shown is a bunch of operations that we can do on a map. We've shown how we can write values to the map. We've shown how we can read the tree head from the map and how to get a specific verified value from that map. We've looked at how to sort of switch to some of these substructures for that map. And when you're using the REST API or the client libraries, the set of operations that you do to the logs for the map are exactly the same as the set of operations to do to a regular log. So once you have that knowledge built up once, you can reuse that in the other aspects as well. The final part on maps is similar to logs. If we go back up to where we select the map that we're interested in looking at, before we created that new map, but now we can go back and we can say, hey, list existing maps, and here we can see the map that we created and we can go straight to it, or we can load it by name. So thanks for bearing with us so far. The next tutorial we'll look at is we'll talk about object hash, JSON, and we'll touch on redactable types as well.